Hello, this is Cameron Urban, and this is my MEMS 101 Sandbox project. For this project, I decided to build a clapped-activated light switch. So the requirements that I laid out at the beginning of this project were that the installation couldn't be too intrusive. So, as you all know, as WashU students, we are not allowed to do certain things to our dorm room. So I didn't want to break any of those requirements. Like, for example, I didn't want to have to put any holes in the wall or anything like that. I also couldn't actually access the actual wiring of the light switch. I also wanted to use a commercially available and easily available microcontroller, so I decided to use an Arduino Nano. So the entire project was open source, and I accomplished that by making a public repository on GitHub where anyone can download the code I wrote if they decided to make one of these themselves. So why did I decide to do this project? The main reason is because of a growing commercial interest in home automation. And this has led to an increase in my interest in home automation. Some of the popular products that have come out recently that have sort of moved us towards living in fully automated houses are the Amazon Echo, which is constantly listening to what you say. And if you call on it by saying Alexa, for example, you can ask it to do certain tasks. So it's almost like it's really fascinating. It's like a everyday man's artificial intelligence. Hue is a subset of the Philips company, and they make intelligent LED light bulbs that you can sort of auto adjust the hue of the lighting in a particular room. I believe there's a bunch of other functionality to them as well. Nest is a smart thermostat that sort of controls the way you heat and cool your home to sort of in a very user-friendly and energy-efficient manner. So the first of the three main things that I learned about while researching this project are continuous rotation servos. So previously, I had only used position-controlled servos. So they cannot rotate past 180 degrees normally. And when you actually write their positions, when you actually code into the Arduino IDE what position they should move to, you give it a particular position. With continuous rotation servos, you don't do this. Instead, you actually you tell it which way to turn and for how long to turn, and that's your entire control of the system. So this was really fascinating, and it was very educational to sort of understand of. Yes. However, compared to the position-controlled servos, there are some issues that arise from you don't actually have any feedback about where the Arduino is. So in your code previously with the other type, you could simply store the position in a variable and then just access that whenever you want. But here, you sort of have to like find out experimentally where you want the servo, like where the servo is, and look at it from that sort of standpoint. And the particular servos I used for this project were two SM3433R high torque continuous rotation servos. And the data sheet for these servos is linked to at the very back in the reference slide. So the second thing I learned about was Arduino Nano Analog Inputs. So this project contains a Electret microphone, which I'll talk about soon. And essentially, I'm pulling data from that microphone in the form of a voltage that it is supplying. So that voltage ranges from 0 to 5 volts, and it's automatically converted by Arduino into an integer from 0 to 1023, so a 10-bit integer. Yes, and the method that you use to actually access this is you pull a analog read, and then the particular pin, the particular analog pin on the Arduino Nano that the microphone output is connected to. So in my case, I used A0, which you can see on the diagram at the bottom of the slide. So the third thing was Electret microphones themselves. So I've never actually worked with a microphone on an Arduino, so this was really fascinating to sort of get to experiment with and see exactly how they work. So the way electric microphones work is that they essentially, the variations in sound pressure cause a flexible metal diaphragm to vibrate back and forth. And this metal diaphragm acts as one plate in a parallel plate capacitor setup. And when it vibrates, it decreases or increases the distance between the two plates in this capacitor. This varies the output voltage, as many of us have learned in physics, of the system. This voltage is then put through a transistor to amplify that signal, and then is outputted to the Arduino, which then converts that voltage into that 10-bit 0 to 1023 integer. So one of the most challenging parts of this project was actually designing and machining the enclosure. So here we can see how it's done. So in the render, which is the image on the right, there are three objects. So the one farthest to the right is a small aluminum plate that I'll talk about in the installation video. And what this this actually fit behind a plate that was already screwed into the wall. So this is actually the plate that your light switches are mounted to, and that's the middle item in that image. So this plate is behind that plate, and it has a tapped hole in the middle of it, and a machine screw goes into the enclosure, which is the furthest to the left object in the image, into the hole in the and into that tapped hole, and it sort of holds it all to the wall. And I found this was a very effective way of mounting things to the wall without actually having to drill a hole in the wall, which would violate our res life rules. So the enclosure itself, so the farthest to the left object, I actually bought off a SparkFun, I believe, and then I laid up this design of it in SolidWorks and added all of those slots and holes you see. So the square slots on the front of the enclosure, those are where the servos fit in, and the mounting screws to them screw into those little holes by the square slots. Included in this design are also a square slot in the side, which was how I plugged in the Arduino into my computer to program it, even while it was mounted inside the case, and also a hole in the side and the bottom for the wires from the battery supply to come up into the enclosure. And there are also two holes in the front that are at sort of a diagonal, and those two holes were how the wire from the two servos came in and connected to the Arduino inside the enclosure. All of this will become more clear when I walk through our circuit in the upcoming video. This is my MEMS 101 Sandbox project. It is a open source Arduino controlled clap activated light switch. So this here is the outer enclosure that you saw a few slides back. It is made of aluminum and machined to include the holes for servos, the holes for their leads, a mounting hole with a 1/4-20 screw, and a hole down here that you can't see right now that lets the lead in from the battery source. So let's walk through the circuit. So this here is our batteries, or our batteries. They are 4 AA batteries in series, so that produces a relatively constant 6-volt power source. This goes into the voltage in and ground pins on the Arduino. From there, the Arduino produces 3.3 volts, which powers the Electret microphone right here, and 5 volts, which powers the two servos. For this demonstration, only the upper servo is in use because there are some technical difficulties with the lower servo. So, when the Electret microphone senses a voltage of a certain level, that voltage is outputted into this analog read pin in the Arduino. That Arduino then tells the servo to rotate at a certain speed for a certain time. That causes this servo horn to rotate 90 degrees till this servo horn is touching this back wall, which turns the light switch. The next time it rotates, it'll rotate the opposite direction, 90 degrees back here, turning the light switch to the opposite position. Let's install it. So at this point, we've installed our light switch module. The way we did that is that we just unscrewed the strike plate from the wall, and behind the strike plate, I inserted a machined aluminum piece that was in that assembly render that you saw a few slides back that had a 1/4-20 tapped hole in it. We then screwed this piece this machine screw right here into that hole, and that holds it all into place on the wall. So let's see it work. So it has an on switch right here on the battery source. When you see the lights flashing, it indicates that the Arduino is reading the input from the microphone and that it's ready to function. So and that is my project. Thank you for watching. So after that video, as you may have noticed, there are still some issues with this design. So for example, it was a little difficult to get both servos to work simultaneously because they were rotating in opposite directions, so they would turn one light on and one light off, and that's obviously not ideal. So implementing that into the code is an issue that I'm still working on. Besides that, there's this idea of double clap sensing. So right now, the code only looks for a noise above a certain, the outputs a voltage above a certain known value. So the issue is that then if any sound goes off in the room that's louder than your clapping, like for example your door opening or closing, it will also be registered as a clap and the light switch will activate. One way to get around this is to actually register, to only detect a clap if two two consecutive loud noises are recorded. So for example, clapping twice. This is a little challenging to implement, and so I decided not to do it for this project just because it would require more debugging. Another thing that would be interesting is using a transistor or a relay to actually directly act as an electronic switch in the actual circuit to turn the lights on or off. I obviously could not do this because this would require flipping off the breaker for my dorm room, which I am apparently not allowed to do. And yeah, so that would be an interesting thing to do at your own home. A similar thing that you could do at your own home is actually use the light switch wires themselves as a power source for the enclosure and for the entire module. So I have an external battery source for this, but that seems sort of silly when I have a 120 volt power source that I'm literally right next to. What you need for this is essentially a 120 volt AC 60 hertz to 5 volt DC step down converter, which would be a little expensive, I think, but I think that it would be worth it, just being able to get rid of those batteries hanging off the bottom of the enclosure. Another thing that would be great would be to have two buttons on the outside of the enclosure that, if you pressed, would act as a clap activation for a particular switch, and that way you could actually turn the lights on and off just by flicking the switches, just like you normally would. And that way, in case you ever wanted to sort of manually do the lights because you're right next to the light switch and you don't want to clap, that way you'd have the ability to do that. So here are my references. The references for each picture, these were all pulled from these particular websites. And my research data was all these. The items in blue are items that I recommend you read. Really fascinating information. The Arduino Nano information is just great. It's a great microcontroller. I really recommend it for any small project you want to do. And the repository link is at the bottom. And if you would like to look at my code, you can just copy and paste that URL, and it will take you right to it. Well, thank you very much, and that's my project. Have a good night.